This next demo is the ring launcher. So the ring launcher, as the name indicates, will launch rings. So I've got several different examples here. So I'm going to start with these two. So here we have a piece of copper and a piece of aluminum. You'll notice the same diameter. They are the same height. Right? Really the only difference is they're made out of two different materials. So I have a magnet here. Is it attracted to the copper?
No.
Oh, okay. Is it attracted to the aluminum?
No.
No. So both cases, they don't feel any push or pull from a magnet. So I'm going to start with the copper because what this ring launcher has, it has a coil of wire. Hopefully you can see the wire coiled around here. And I have it plugged into the wall outlet, which means we're getting which type of current?
Alternating.
Alternating current, that's right. So we have alternating current running through this coil. Well, when I push the button. Alternating current will run through the coil, which means its magnetic field will change with time, which means when you have a changing magnetic field on a conductor, that's going to induce a current that will also alternate with time, just like this. But remember, it's one of those weird things about electromagnetism that if you have a current flowing, it will cause its own magnetic field. In the case of this magnetic field, the second one, will always be in opposite direction to the first. All right? So, as a result, these two magnetic fields will repel. Pretty simple. So when I push down this button, you should expect this copper cylinder to do what?
Move up.
Move up. It's repel. It can only move up because that's how it's set up, right? So, let's see what happens. So I'm going to push the button, all right? So 3, 2, 1. Ooh, amazing. So let's see it again. So what about this high? How high would we estimate that? Foot?
A foot.
Foot, 12 inches? So now I'm going to try it again with the aluminum ring. So I want you to predict, is it going to go the same height? Will it go higher or will it go lower? Now, those are really the only possibilities, higher, lower, or the same. But when you look at this, it's an interesting question because, first of all, they're not the same material. I started with the copper because we all know that copper conducts electricity very well. Aluminum is a metal, will also conduct electricity, just not as well, as far as I know, not as well as copper. So the result is, okay, well, you would expect it to not go as high because it's not going to have as much current. However, we should also know, when you volunteer, hold these. What do you notice about those two?
This is a lot heavier.
Yeah, the copper is heavier than aluminum. So it has less mass, it's less dense. And since we're throwing something up against gravity, obviously that's going to have a factor. So there's two factors. This has less mass, but will also probably conduct less current. So the less mass would make it go higher, but the less current you would assume would make it go lower. So the question is, which is going to happen? So let's go back to the copper one for reference. So it goes about this high, right? All right, you ready? Make a prediction.
Higher.
Lower.
All right, here we go. 3, 2, 1. Does it go higher or lower than the same?
Go higher.
Higher.
A little bit higher, right? So even though it may not conduct electricity as well because it has less mass, and it's pretty significant how much less mass it is, so it can go higher. All right, so that's our first test. Our next test, I have another aluminum ring. It's the exact same height. It's the exact same diameter, right? But you also notice that it has a hole in it. So now, technically, it has less mass than this one. So the question is, will it go higher, lower, or the same? So if we have this guy for reference, so it goes about this high, right? So let's do this other one. All right? Make a prediction. Higher, lower, or the same?
Higher.
Lower.
Lower would be correct. It doesn't go anywhere because no current can flow, therefore no magnetic field, no repulsion. So this second aluminum ring demonstrates that you need current. All right, so this guy's going the highest, so I have one more aluminum ring. Notice it has the same diameter, right? But it's not the same height. It's literally half the height. Okay, well again, I'm definitely reducing mass. So, make a prediction. Let's go higher, lower, the same. So here's the original. It was about this high. And here's the other one. So higher, lower, or the same.
Higher.
All right.
Oh my goodness.
Do you go higher, lower, or the same?
Lower.
It was definitely lower. Thus showing that it is the current. So I said, oh, the current didn't seem to make that much of a difference between my copper and aluminum. It did, but it had a lot less mass. This has literally half the mass of this, but this one still went higher because we can get more current. All right? Now, got two more little experiments here. When we did these experiments or demonstrations earlier, we had the AC electromagnet and the DC electromagnet. Both of those were coils of wire wrapped around an iron core. And we've learned that iron is not necessarily a magnet by itself. It can be if the domains are aligned and all that. But iron by itself isn't necessarily a magnet. So again, I have a piece of iron. It's not a magnet, but if I put a magnet on it, it'll be attracted. Because we can make its domains align. What I'm going to do here is I'm going to put that iron in the middle of this ring launcher. Just like with the electromagnets, we wrap those specifically around iron. Because when this thing gets magnetized, we can magnetize the iron, and the iron will actually magnify or add to the magnetism of the coil. So, let's see if this iron makes any difference. And I'm telling you, it should. So, that's my prediction. This will add more magnetism, therefore we'll see a slightly different behavior. So let's do our control essentially here. It goes about this high. So I'm saying that it should give us a stronger magnetic field. So my question for you would be, is it going to go higher, lower, or the same?
Higher.
All right, let's see.
Whoa.
This one originally went about this high, now it's going how high?
More than twice that.
Yeah, it's literally bouncing off the ceiling, which is that noise you can hear. So by simply adding the iron core here, we can really increase our magnetic field. Now the last demonstration with the ring launcher is not launching the ring at all. It's induction. So here we have a circuit. So notice that we have a coil of wire, and the two ends of the wire attach right here so that I can attach this light bulb. So I'm going to take my light bulb, put it right in there. If you look, there's no batteries, there's nothing else on here. There's no reason for this to light up. But when I put a coil of wire in a changing magnetic field, it will cause current to flow, and again, it has its own opposite magnetic field, which will push back against it. But I'm not going to let this shoot off because it's a light bulb, and that would be bad. I'm just going to hold it here, but I want you guys to see that current is induced in this loop. All right? Turn around this way. So notice that as I get closer to the coil down here, it gets brighter because the magnetic field is weaker the farther you are away, and it's stronger closer. So as I get close down here, I can only put it this far because if I got any closer. You notice how it was getting bright. It'll get so bright this bulb will burst. So it's designed to not do that. But notice again, if I take this iron core out and try to do it, it's not strong enough to even light it. But with the iron core there, it amplifies our magnetic field, and we get the electromagnetic induction that causes the light to light.